Let's discuss a question from radiation, heat transfer radiation. So it's a question on black body. A black body is at a temperature of 2880 Kelvin. The energy of radiation emitted by the object in the with wavelength range is U1, and in the certain range it is U2. So you are asked briefly about U1 and U2. In which of the wavelength range it emits more radiation, and the Wien's constant is given. Now we need to understand, before coming to this question, we need to understand, because we don't know at this temperature where it emits, at what wavelength it emits maximum radiation to. So this can be known easily by Wien's displacement law in radiation. Displacement law, which basically says lambda max, that is the wavelength at which it emits maximum radiation, and a given temperature. So at a given temperature you can always find out the wavelength at which it emits maximum wavelength. And the beautiful thing is that this Wien's displacement law says that this product of this wavelength at which it emits maximum radiation at a given temperature T, this product lambda T is constant, and that constant is basically the Wien's displacement law. So we'll use this to find out lambda max. The temperature is 2880 Kelvin, and the Wien's constant, which is given in the question, is 2.88 into 10 power 6. So from this you will get to know that lambda max is, so this is 2880 into 10 power 3 by, you have the 2880, so this means it is 1000 nanometer. So if you remember the Planck's distribution curve, which basically plots the spectral density, remember this is spectral density, it's not the emissive power, it's the spectral density, which is per unit wavelength. And if you look at the plot of spectral density with wavelength for different temperatures, there are curves like this, but let's plot it for a given temperature. It just behaves like this. This is a general trend. So this wavelength, so this curve is for 288. I mean, there are different curves for each of this temperature, and as the temperature increases, the peak shifts to lower wavelengths. That's what you would have studied. So at this wavelength, it is 1000 nm. So that's what the Wien's displacement law gives. The wavelength at which, at this temperature of 2880, the wavelength at which the spectral density is maximum is 1000 nm. Now what he is asking is, between 499, let's say the 499 is somewhere here. So between this 499 and 500, so there is just a wavelength range of 1 nanometer, okay, nanometer, and between 999 and 1000, so it will be just 1 mm below the peak. So in this range of, both are 1 nanometer, so in this range, which emits more which emits more radiation? So it's clear from the graph. Remember, another important concept is that this is just the density, okay, the spectral density or power per unit wavelength, but the area is what, area of this curve gives the energy, emissive power. This curve gives the emissive power at that wavelength, at that temperature, sorry, because at this temperature, let's say you want to find out the total emissive power at temperature of 2880, then area under the total curve will give you, so that will be the emissive power at that temperature covering all the wavelength range, emitted in all the wavelength range. Now in this wavelength range, in this 999 to 1000, the area is greater than between 499 to 500, obviously you can see. So I can say that energy emitted in between 999 to 1000 nm, that area is more than U1, which is between 499 somewhere here, which I have drawn, this area is obviously less than the area of this. So 499 to 500 nm. So this area is obviously less than the between 999. So the amount of energy emitted in 999 to 1000, obviously this can be seen because it peaks at 1000. So between 999 and 1000 it will emit more energy than somewhere far away. So U2 is more than U1. This is a very good question, conceptually a good question. Thank you. Answer is option is D. Thank you.